Jupiter looks beautiful from far away, but it is one of the most unforgiving places in the solar system. There is no solid surface to land on, no safe path through its crushing atmosphere, and no easy way back once a mission goes too deep. Tonight, this journey moves layer by layer into the giant planet to understand why Jupiter is not just hard to reach, but why it may truly be a one-way trip. Before beginning, please like the video, subscribe to the channel, and settle in for a quiet descent into the largest world orbiting the Sun. Jupiter remains far from Earth in a way that changes the meaning of travel before any spacecraft leaves the ground. It is the fifth planet from the Sun, settled in the outer solar system at an average distance of about 778 million kilometers from the Sun. From that range, sunlight takes about 43 minutes to arrive there. The fact is simple, but it sets the pace for everything else. Jupiter exists under the same sun that lights Earth, yet the connection is stretched. Light is slower in feeling when it must cross such a gulf. Warmth is weaker. Signals take longer. Every useful action must account for the distance first. Seen from Earth, Jupiter often appears bright and steady. It can stand out more clearly than many stars. This brightness can give the wrong impression. It suggests presence, even closeness, as if the giant world is only a little farther away than Mars or Venus. In reality, Jupiter shines not because it is near, but because it is enormous and reflective. It is the largest planet in the solar system. More than 1,000 Earths could fit inside it if it were hollow. Its width is about 11 times that of Earth. A distant object can still dominate the sky if it is big enough and reflects enough light. Jupiter teaches that lesson with unusual clarity. At its orbit, sunlight has thinned greatly. The Sun still rules, but it no longer floods the surroundings with the same strength felt near Earth. The clouds of Jupiter receive only a small fraction of the sunlight that reaches Earth. Day exists there, but it is a colder day. The planet is not dark in the absolute sense, yet it belongs to a dimmer province of the solar system. Solar energy weakens with distance because the same light spreads across a widening sphere. By the time that sphere reaches Jupiter's path, the brightness per unit area has dropped sharply. A mission travelling there moves outward not only across distance, but into reduced light and reduced easy power. This has practical consequences long before arrival. A spacecraft bound for Jupiter must carry a different idea of endurance than one meant for the inner solar system. The voyage is not a brief crossing between neighbouring worlds. It is a sustained passage through deep interplanetary space, where sunlight is weaker, temperatures are lower, and resupply is impossible. Systems must continue working through years rather than weeks. Small faults have more time to grow serious. Spare margins matter more. Reliability stops being an added virtue and becomes part of basic survival. The scale of the journey is visible in the history of robotic missions. NASA's Galileo mission leaves Earth in October of 1989 and reaches Jupiter in December of 1995. NASA's Juno mission leaves in August of 2011 and arrives in July of 2016 after a journey of about 5 years. These are not slow because engineers forget how to build powerful machines. They are slow because Jupiter is truly far, and because space travel follows orbital paths shaped by gravity around the Sun rather than a straight line through still air. A spacecraft does not point at Jupiter and drive forward in a simple sense. It enters a long solar curve and meets the planet where the mathematics of motion allows. That distinction matters for any return. Distance in space is not just length, it is also timing. Earth moves. Jupiter moves. The Sun remains at the centre of both orbital paths. A mission must leave at the right moment, travel along the right path, and arrive when the target world is there to be met. The same truth applies again for a trip home. Return does not mean turning around on the spot. It means beginning a second interplanetary journey under equally strict timing. The outward distance is already severe. The repeated precision required for a round trip makes it more severe still. Communication also changes character across that scale. Radio signals move at the speed of light, which is extremely fast but not instant. Between Earth and Jupiter, the delay grows into long minutes, depending on the positions of the planets in their orbits. That delay does not simply inconvenience conversation, it changes operations. Fast back and forth guidance becomes impossible. A crew near Jupiter could not rely on constant immediate support from Earth during every problem. Machines, procedures, and people would all need greater independence because the gap itself inserts waiting into every exchange. This remoteness helps explain why Jupiter is often misunderstood. It is sometimes described as a failed star, but it is not one. It does share broad ingredients with the Sun, especially hydrogen and helium, yet it does not have enough mass to ignite sustained fusion and become a star. It forms as a planet, not as a small star that almost succeeded. The distinction matters because Jupiter does not need to be a star to create star-like difficulty for travel. Distance alone gives it that power. The planet sits far enough from Earth and far enough into the outer system that the journey begins to resemble an expedition into another regime of the solar system, rather than a visit to a neighbouring world. Even this outermost view, before attention settles on gravity, magnetism, radiation, or atmosphere, already carries a quiet finality. Jupiter is not merely a place that takes a long time to reach. It is a place whose distance steadily converts ordinary mission problems into structural ones. Power systems must adapt to dimmer light. Hardware must last for years. Communication must accept delay. Navigation must respect moving planets and narrow launch windows. Human life support, if it were ever attempted on such a route, would have to survive inside a sealed machine for spans that change the psychology and logistics of the mission itself. Nothing about the gap is dramatic in appearance. It is only black space, thin sunlight, and a bright planet far ahead. Yet that calm exterior hides the first reason Jupiter becomes a one-way trip. The journey outward is already so long, so cold, and so strict that return stops being the natural second half of travel and becomes another major mission of its own. Jupiter's distance is only the first difficulty. Its mass is the next. The planet contains about 318 times the mass of Earth, and more than twice the mass of all the other planets combined. That mass gives Jupiter a gravitational reach unlike that of any other planet in the solar system. Gravity is the attraction between masses. In daily life it is felt as weight and falling. In space it is more exact and more patient. It bends paths over great distances, controls speed without touch, and decides how much energy must be spent to arrive, to stay, and to leave. A useful term here is gravity well. A gravity well is not a real hole in space. It is a simple way to describe how strongly a massive body holds nearby objects. The deeper the well, the more energy is needed to climb back out. Jupiter's well is deep because the planet is so massive. A spacecraft can use that depth to gain speed on the way in, but the same gain becomes a penalty if the craft later tries to slow down, rise away, and return toward Earth. In that sense, Jupiter is generous only in one direction. It helps bodies fall inward. It does not help them leave. Approach to Jupiter therefore means more than covering distance. It means surrendering energy to the planet's pull and then paying that energy back if orbit or escape is required. A spacecraft coming from the inner solar system arrives already moving around the Sun, and Jupiter's gravity adds to the complexity of that motion. The path curves inward. Speed grows. The closer the craft comes, the harder it is to remain merely nearby, to stay in orbit. The craft must lose enough energy to become bound to Jupiter rather than continue past it. To leave again, it must regain that energy. Each part of the process has a cost. This is why simple ideas of arrival do not apply well to giant planets. Near Earth, it is easy to imagine travelling somewhere, pausing, and later departing by reversing the trip. At Jupiter, every kilogram of spacecraft mass presses against that idea. Engines, fuel tanks, shielding, instruments, life support, structure, and reserves all add weight. In mission design, the important point is that more mass requires more propellant for the same change in speed. More propellant then adds more mass, which calls for still more propellant. The cycle grows quickly. Jupiter's gravity does not create this logic by itself, but it makes the logic severe. At the level where gravity near the top of Jupiter's atmosphere is often compared with Earth's, the number can seem almost manageable. The gravity there is about 2.5 times that of Earth. That sounds large, but not impossible. The deeper truth is that this familiar comparison is not the main issue for travel. The real problem is the scale of the planet and the depth of its gravitational field. Jupiter's escape speed near the 1 bar level is about 60 kilometers per second, far above Earth's. Escape speed is the minimum speed needed to break free without further propulsion. It is a useful measure of how tightly a world holds nearby motion. Jupiter's large value reveals the central difficulty. Leaving is expensive. This expense begins to matter well before any deep descent. Even a spacecraft that never enters the atmosphere must deal with the energy demands of capture and departure. Robotic missions can do this because they are comparatively light, highly specialized, and often designed around narrow scientific goals rather than return. Galileo reaches Jupiter and becomes an orbiter only by carrying the fuel and planning needed for that single purpose. Juno follows a carefully shaped mission and remains focused on observation, not landing, not ascent, and not transport of living passengers. A crewed mission with the mass needed to preserve human life over years would not be merely a larger version of those spacecraft. It would be a different class of problem. Jupiter's gravity also governs a vast surrounding region in which passing bodies can be redirected, captured for a time, or flung away on new courses. That broad gravitational domain is often described through the Hill sphere, the region around a world where its pull can dominate the motion of smaller nearby objects against the competing pull of the Sun. For Jupiter, this region extends across tens of millions of kilometers. It is not a wall and not a boundary that can be seen. It is a measure of influence. Within such a region, motion increasingly belongs to Jupiter's system rather than to simple solar orbit alone. A spacecraft entering it is no longer just travelling through outer interplanetary space. It is entering the giant planet's own dynamical realm. That realm has shaped the solar system for billions of years. Jupiter perturbs asteroids, redirects comets, and acts as a major architect of orbital motion in its neighbourhood. Some small bodies gain speed from close passages and are thrown outward, some are drawn inward onto new paths, some become temporary captives. A spacecraft follows a calculated route rather than a natural one, yet it remains subject to the same underlying physics. Jupiter is not an object that waits passively to be visited. It is an active gravitational presence. For a human mission, this transforms the meaning of return. A return from Jupiter would not simply require surviving the outward journey and the conditions near the planet. It would require retaining enough propulsive capability after years in deep space to climb back out of one of the deepest planetary gravity wells in the solar system. Any plan involving descent makes this harder still, because every lower layer entered is another layer from which energy must later be purchased with fuel that must somehow already be there. The problem becomes circular. The vehicle must carry the means of escape into the very place that makes that escape most difficult. This is why Jupiter begins to feel like a one-way trip, even before any attention turns to radiation or atmosphere. Distance stretches the voyage. Gravity changes its logic. The planet's mass bends paths, raises speeds, deepens the energy cost of every maneuver, and turns return into a far more demanding mission than arrival. In the wide space around Jupiter, nothing dramatic needs to happen for the trap to begin. The trap is already present in the mathematics of falling towards something so massive that coming back demands almost as much from engineering as going there in the first place. Beyond Jupiter's broad gravitational reach, the planet begins to reveal something else. It is not a single world standing by itself in empty space. It is the center of a system. Around it move moons, small bodies, and many lesser objects spread across distances so wide that a spacecraft can already be within Jupiter's family of orbiting companions while still feeling far from the planet itself. This outer Jovian system is quiet in appearance. There are no sharp edges in the darkness and no visible fence around the planet. Yet the region has structure. Motion there belongs increasingly to Jupiter, and the scale of that structure adds another layer to the idea that Jupiter is not a place simply reached and left. NASA now counts 95 moons officially recognized around Jupiter, and even that number does not capture the full setting. Thousands of small objects also travel in the planet's orbital realm. Some are too small to be called major moons in any practical sense, yet they are part of the same broad family. This makes Jupiter less like a lone destination and more like a miniature planetary system nested inside the larger solar system. A mission approaching it does not move directly from open, interplanetary space to the cloud tops of one giant planet. It enters a wide orbital province populated by many companions, each following its own path. The first important distinction among these moons is between regular and irregular orbits. A regular moon generally follows a path close to Jupiter's equatorial plane and often moves in the same direction as the planet's rotation. An irregular moon does not. Its orbit is usually more tilted, more stretched into an ellipse, and often backward relative to Jupiter's spin. Backward motion in this sense is called retrograde. Many of Jupiter's distant outer moons are retrograde. That unusual pattern tells part of their history. Observations indicate that the larger outer moons are likely captured asteroids, while many of the smaller ones are probably fragments left from collisions long ago. In the far Jovian system, the outer population looks less like a tidy set of bodies born quietly in place, and more like a record of capture, breakage, and rearrangement. This matters because it changes the geometry of approach. Around Jupiter, the wider system is layered. There are many orbital paths, inclinations, and groupings to account for. The outer moons do not form a crowded swarm in the ordinary sense. Space remains overwhelmingly spacious. The difficulty comes from scale rather than congestion. A spacecraft can travel for immense distances inside the Jovian system without being near the visible planet. The emptiness is still there, but it is organized emptiness. with moving bodies spread across it like distant markers in a giant rotating map. Most of the small outer moons orbit much farther out than the 4 Galilean satellites. Those 4 large moons, discovered in 1610, are the best-known members of the Jovian family. Yet they do not define the whole system. Beyond them lies a much broader realm of lesser bodies, many gathered into loose orbital groups that share similar tilt and direction. These similarities suggest common origins. A parent body may have been captured and later broken apart, leaving a family of smaller moons to continue on related paths. Over time, Jupiter's far outskirts become a museum of ancient impacts and captures, written not in rock layers but in orbital patterns. Even the large moons show how much room exists around Jupiter. Callisto, the outermost of the 4 Galilean moons, circles the planet at about 1,883,000 kilometers. That is already a distance greater than the span from Earth to the Moon by several times over. Yet within the Jovian system, Callisto is not the far edge. It is only the outermost member of the inner major family. Many smaller moons travel much farther out. The distance between Jupiter and its most familiar large moons is therefore enough to contain entire Earth-Moon scale comparisons. And still the outer system continues well beyond. For a spacecraft, that breadth changes what arrival means. A vehicle can cross into the realm of Jupiter's moons and still have a long way to go before the planet becomes a nearby object. This is one reason the phrase Jupiter system is often more accurate than simply Jupiter. The destination is not only the planet, it is the whole environment of bodies moving around it. When New Horizons used Jupiter for a gravity assist on its way outward, its closest approach to Jupiter was about 2,300,000 kilometers, only a little beyond Callisto's orbit. Even at that distance, the spacecraft is already engaged with the Jovian system in a meaningful sense. Yet a great deal of orbital space still lies between it and the cloud tops. The outer moons themselves are generally small and dark compared with the Galilean satellites. Many are thought to be captured objects from elsewhere, shaped more by ancient impacts than by internal activity. Their importance in this far region is not beauty or geological complexity. They show that Jupiter's outer surroundings are not an empty moat around a central body. They are a distributed system extending across millions of kilometers, where even minor objects help define the planetary realm. This broad arrangement also carries a quiet operational burden. Navigation near Jupiter cannot assume a single target with nothing else of consequence nearby. Planners must account for many orbital tracks, long timing arcs, and the fact that meaningful activity occurs across a system of great depth. A route that seems to pass only through emptiness is still passing through a space that belongs dynamically to Jupiter and is shared by many moons on different planes. The challenge is not traffic in the human sense. It is the requirement to respect a large three-dimensional architecture. So the far Jovian system introduces a new kind of distance. The voyage from Earth to Jupiter is one distance. The spread of Jupiter's own family around the planet is another. These distances stack on one another. A mission can solve the first and still confront the second. Long before a craft reaches the visible bands of the giant world, it has already entered a realm of scattered companions, ancient captures, and immense orbital spacing. In that broad darkness, Jupiter begins to feel less like a planet waiting ahead and more like the center of a remote kingdom whose outer members arrive first, quietly enlarging the scale of the journey before the planet itself is truly near. Before Jupiter's great magnetic domain is entered, there is a front line in space where the outward flow from the Sun can no longer continue unchanged. That front line is the bow shock. It is not made of rock, ice, or gas in the ordinary sense. It is a moving shock boundary formed in plasma, the charged state of matter that fills the solar wind. A shock is a sudden change in conditions such as speed, density, pressure, and temperature. Around Jupiter, the bow shock forms because the solar wind races outward through the solar system at very high speed and then meets the giant magnetic obstacle presented by Jupiter's surrounding field. The wind cannot pass through that obstacle in the same simple way it crosses ordinary open interplanetary space. It must slow, compress, and reorganize. The word bow is helpful. It comes from the curved wave at the front of a ship moving through water. Around Jupiter, the shape is similar in principle but very different in substance. There is no liquid sea there, only thin charged particles moving through space. Yet the pattern remains. The solar wind streams outward from the sun, and ahead of Jupiter's magnetic barrier a curved shock front stands in the flow. It is a standing structure in the sense that it remains associated with Jupiter, even while its exact position changes. The shape bends around the planet's sunward side and deflects the incoming plasma around the obstacle, rather than allowing it to continue straight through. This makes the bow shock the first clear sign that Jupiter is no longer only a distant planet with moons and gravity. It is now an active space environment that changes the character of the solar wind itself. Before this point, the solar wind remains fast and relatively undisturbed on the scale of Jupiter's local system. At the bow shock, that flow changes suddenly. The plasma becomes compressed. Its speed drops from supersonic to slower flow. Supersonic here means faster than the speed at which information about pressure changes can travel through that plasma. Once the flow reaches the shock, it can no longer ignore the obstacle ahead. The system forces a transition. In ordinary air on Earth, shock waves often depend on frequent particle collisions. The Jovian bow shock does not work that way. Space around Jupiter is too thin for ordinary collisions to do the job efficiently. For that reason, it is called a collisionless shock. The word sounds paradoxical at first, but the idea is steady. The particles do not need to strike one another often like molecules in thick air. Instead, electric and magnetic fields organize the change. Charged particles respond to those fields, and through that collective response the flow is slowed and heated. The shock is real, abrupt, and powerful, even though the space around it remains extraordinarily thin. This region is not visible to the eye, but spacecraft can hear and measure its passage in the language of instruments. Juno's waves. Investigation recorded distinctive changes as the spacecraft crossed Jupiter's bow shock in June of 2016. The data reveal a transition from the quieter upstream solar wind to a region of much more disturbed electromagnetic activity. Human senses cannot stand in that place, but the instruments reveal a boundary alive with turbulence as wave energy and abrupt change. The crossing is not symbolic. It is a measurable event in the physics of the planet's outermost space encounter with the Sun. The location of the bow shock is not fixed. It moves because the solar wind itself is variable. The Sun does not send out a perfectly steady stream. Solar activity changes, density changes, speed changes, magnetic conditions change. When the solar wind presses harder, Jupiter's bow shock is driven closer inward. When that pressure weakens, the bow shock can stand much farther out. Earlier missions show just how large these shifts can be. Pioneer 11 crossed Jupiter's bow shock more than once, revealing that the boundary moves as the giant magnetosphere responds to solar conditions. Ulysses encountered it at a distance farther out than earlier expectations during one pass. likely because the solar wind pressure was unusually low. So even this first boundary is not a stable shell. It breathes with the sun. That variability matters for travel. A spacecraft cannot rely on a single permanent map of the bow shock's position. It can only predict a likely region based on models and current solar conditions. This introduces uncertainty into the approach. The first true outer frontier of Jupiter is therefore not marked by a line painted in space. It is marked by a zone where the incoming solar wind is forced into a sudden new state, and the exact location of that state may shift by large distances. The approach remains orderly in the language of physics, but it is not rigid. The bow shock also teaches something important about scale. Around Earth, a bow shock exists as well, but Jupiter's is far larger because the magnetic obstacle behind it is so much larger. The giant planet projects its influence so far into space that the solar wind is confronted long before any material part of Jupiter comes near. A spacecraft can still be astonishingly far from the cloud tops and yet have already reached a frontier created by the planet. This enlarges the idea of the destination once again. Jupiter is not only the striped world seen through a telescope, it is a system that begins to announce itself far out in the darkness through invisible but forceful structure. For human travel, the bow shock is not the greatest danger near Jupiter, but it is the first unmistakable transformation of environment. It marks the end of one kind of interplanetary travel and the beginning of another. Before it, the solar wind is the broad background of the outer solar system. At it, the wind is forced to acknowledge Jupiter. The flow becomes disturbed, heated, and turbulent. The quiet simplicity of open space is replaced by the first hard sign that a giant planetary system is taking control of local conditions. So the bow shock stands as Jupiter's outer collision front, a broad curved shock wave written into plasma rather than air, shifting with solar pressure yet always tied to the giant planet's magnetic obstacle. It does not shine in ordinary light and does not offer a surface to touch, but it changes the space around Jupiter in a sudden and decisive way. At this frontier, the road inward is no longer only a matter of distance crossed. It becomes passage through a boundary where the solar wind itself is forced to slow, compress, and yield to Jupiter's presence. Between Jupiter's bow shock and the main magnetic boundary of the planet lies a broad region called the magnetosheath. It is made from solar wind that has already been forced through the shock and changed by it. The particles there are still part of the solar wind in origin, but they no longer behave like the faster outward flow found upstream. They have been compressed, heated, slowed, and turned. The result is a sheath of disturbed plasma wrapped around the outside of Jupiter's magnetic domain. At Jupiter, this layer extends across a vast volume of space and can take a long time for a spacecraft to cross. The magnetosheath is a region of transition, but it is not a narrow line. A line belongs to the bow shock. The magnetosheath belongs to the space after the shock, where the solar wind has already yielded to the presence of Jupiter, but has not yet reached the inner boundary where the planet's magnetic field fully takes command. This makes the region dynamically mixed. It still carries the momentum of the solar wind, yet that motion is being redirected around a giant obstacle. The flow bends. Its pressure changes. Magnetic fields are compressed and rearranged. Turbulence develops. A spacecraft entering this region moves through plasma that remains sparse by earthly standards, but is far more active than the quieter solar wind outside. One of the most important changes is heating. At the bow shock, part of the ordered bulk motion of the solar wind is converted into random particle motion. That random motion is what temperature measures. So the magnetosheath contains plasma that is hotter than the solar wind that approached Jupiter from farther out. Density also rises because the flow has been compressed. Speed drops compared with the upstream wind, but the motion does not become calm. It becomes restless instead. Heated plasma, fluctuating magnetic fields, and changing directions of flow combine to make the magnetosheath a region of continual variation rather than steady passage. The flow there is also diverted around the planet's magnetic obstacle. This gives the magnetosheath a sweeping character. Plasma streams along the outer flanks of the magnetosphere rather than heading straight toward Jupiter. In doing so, it drapes the magnetic field around the obstacle. Draping means that the field lines carried by the solar wind are bent and laid along the shape of the boundary, somewhat like strands of grass pressed around a stone by water. The image is useful because it shows that the magnetic pattern is shaped by the motion of the flow and by the presence of the giant magnetosphere beneath it. This draped and compressed field matters because charged particles respond strongly to magnetic direction. Their paths, pressures, and waves are linked to the field geometry. Inside the magnetosheath, spacecraft measure fluctuations over many scales. Some changes last only moments, others persist much longer. Waves can travel through the plasma. Pressure pulses can move within it. Recent studies have also identified jets in Jupiter's magnetosheath, meaning short-lived flows with unusually high dynamic pressure, the pressure associated with motion. These jets can move either anti-sunward or sunward and appear to be tied to discontinuities and shock-related processes. They show that the magnetosheath is not merely a buffer layer. It is a living plasma environment capable of producing localized surges. The size of the region deepens this point. At Earth, a spacecraft may cross the magnetosheath in a relatively short time. At Jupiter, the scale is much larger. Voyager 2 spent roughly 2 days in the Jovian magnetosheath during its encounter in July of 1979 before it passed through the inner boundary. Juno also crossed from the bow shock into the magnetosheath well outside Jupiter, at a distance of about 128 Jupiter radii from the planet, when it recorded the shock crossing in June of 2016. These examples show that the sheath around Jupiter is itself a major region of space, not a brief interval on the way to somewhere else. Its size and shape are not fixed. Both the bow shock and the inner boundary move as solar wind conditions change, and the thickness of the magnetosheath changes with them. When the solar wind becomes stronger and pushes harder, the whole outer magnetic system is compressed. The magnetosheath can narrow, and its internal conditions can intensify. When the pressure drops, the system expands, and the sheath can become broader. Because the solar wind from the Sun is variable, the magnetosheath is variable as well. Jupiter's rapid rotation adds another layer of complexity. The giant planet spins in about 10 hours, and that fast rotation influences the larger magnetic system pressing against the sheath from within. The outer boundary of the magnetosphere is therefore not just a passive surface holding off the solar wind. It is tied to an internally active planetary engine. The magnetosheath responds to the shape, motion, and compressibility of that engine's outer skin. This helps explain why the region can display rich boundary structure, and why some crossings show extended transition layers rather than a single simple change. For travel, the magnetosheath is not the final barrier near Jupiter, but it already alters the meaning of exposure. A spacecraft in this region must tolerate heated plasma, fluctuating fields, sudden wave activity, and changing flow direction. Instruments must separate environmental signals from spacecraft charging and noise. Surfaces must endure a stream of particles that is not especially dense yet is persistent and variable. For human flight, even without invoking the harsher conditions deeper in, the magnetosheath would already be a place where the environment becomes operationally complex. It does not tear a craft apart by pressure like an atmosphere, yet it steadily acts on electronics, measurements, communications, and planning. So the magnetosheath around Jupiter is best understood as a broad zone of shocked and diverted solar wind, compressed against the outside of the giant planet's magnetic domain. It is hotter than the incoming solar wind, denser than the upstream flow, threaded with draped fields, and alive with turbulence, waves, and occasional powerful jets. Its boundaries move, its thickness changes, its conditions shift with the Sun and with Jupiter's own outer magnetic response. Crossing it is therefore not a simple movement through empty space after the bow shock. It is passage through a vast, active layer where the solar wind is being reshaped into something less direct, less quiet, and more controlled by the presence of the largest planet in the solar system. The magnetopause is the main outer skin of Jupiter's magnetosphere. It is the boundary where the shocked solar wind in the magnetosheath yields to the magnetic and plasma environment, controlled by Jupiter itself. The word boundary can suggest a neat shell around a planet, but at Jupiter the reality is more subtle. The magnetopause is a moving surface shaped by balance. On one side, the solar wind presses inward with its motion and field. On the other side, Jupiter's magnetic field and internal plasma push outward, where these competing influences come into rough balance. The magnetopause stands. It is not solid, not still, and not simple. Yet it marks a real change in who controls the space around Jupiter. Outside it, the Sun still dominates the local flow through the solar wind. Inside it, the giant planet takes over. Because Jupiter's magnetic field is so vast, this boundary lies very far from the visible planet. Juno crossed it on June 25, 2016, at a distance of about 114 Jupiter radii, nearly 8 million kilometers from Jupiter. Even there, the crossing is not experienced as arrival at the planet itself. It is arrival at the planet's rule. That distinction matters. A spacecraft can remain immensely far from the cloud tops and still have entered Jupiter's own magnetic province. The magnetopause therefore enlarges the meaning of Jupiter once again. The planet is not only the striped globe in sunlight, it is also the far-off limit where its internal magnetic power first becomes the main organizer of motion. This boundary is not quiet. The transition detected by Juno is marked by sudden electromagnetic activity, including the onset of trapped continuum radiation. These are low-frequency waves confined within a low-density cavity in Jupiter's outer magnetosphere. Their sudden appearance signals that the spacecraft has crossed into a region where the plasma and field structure are no longer governed mainly by the solar wind outside. At nearly the same time, particle density drops sharply compared with the denser flow outside the boundary. The change is important because it reveals that the magnetopause is not merely a mathematical surface on a model. It separates two physically different domains, each with its own characteristic densities, waves, and patterns of control. Yet the crossing is not always clean. Juno's measurements show that the boundary structure is unexpectedly complex. Different instruments report unusual signatures around the nominal crossing, which suggests that the magnetopause is not always a single thin sheet. It can include layers, folds, and transient structures. This complexity is not surprising when the forces involved are considered. The solar wind is variable. Jupiter rotates rapidly, in about 10 hours and drives internal plasma around with it. The magnetic field is tilted relative to the planet's rotation axis. Plasma from moons such as Io also feeds the system from within. The magnetopause is where all these influences meet. It is a place of negotiated balance rather than rigid separation. Older missions help show the same truth across time. Pioneer and Voyager observations indicate that Jupiter's magnetopause moves inward and outward as the dynamic pressure of the solar wind changes. Dynamic pressure is the pressure associated with bulk motion. When the solar wind arrives stronger and denser, the outer magnetic boundary is pushed closer to Jupiter. When the solar wind weakens, the magnetopause expands outward. This means that the size of Jupiter's magnetic domain is not fixed from day to day. The giant magnetic cavity breathes under solar forcing. A spacecraft approaching Jupiter is therefore not aiming for a permanent line in space. It is approaching a frontier whose position depends partly on the current state of the sun's outflow. The shape of that frontier also matters. Like the magnetosphere as a whole, the magnetopause is compressed on the side facing the sun and stretched into a long tail on the far side. Even on the day side, it is not expected to be perfectly smooth. Models and observations point to asymmetry, with the exact form affected by solar wind conditions, internal plasma pressure, and rotational dynamics. A boundary around such a rapidly spinning and internally loaded magnetosphere cannot be expected to behave like a simple inflated bubble. It is more like a vast membrane under stress, pulled and pressed by forces from outside and inside at once. One reason this membrane remains active is that magnetic fields can interact across it. When field lines from the solar wind and field lines associated with Jupiter meet under the right conditions, they can reconnect. Magnetic reconnection is the breaking and joining of magnetic field lines in a new pattern, allowing energy and plasma to be transferred across a boundary. Evidence of such magnetic merging has been discussed at Jupiter since the earlier spacecraft era. The idea is important because it shows that the magnetopause is not a perfect shield. It is a boundary that can open locally, exchange energy, and rearrange itself. The giant planet holds back the solar wind, but not in a completely sealed way. For travel, this makes the magnetopause a difficult kind of frontier. It offers no hard impact and no visible horizon, yet it marks a change in environment that affects instruments, interpretation, planning, and risk. Outside it, the spacecraft is still in solar wind-dominated space. Inside it, the craft enters a lower density cavity ruled by Jupiter's field, waves, and internal plasma circulation. The crossing may happen once, or a moving boundary may lead to repeated encounters if conditions shift. A vehicle must therefore be prepared not only for entry, but for ambiguity around entry. The boundary can announce itself through wave signatures and particle changes, yet the exact structure may remain complicated even after the crossing is recorded. So the magnetopause is Jupiter's true magnetic frontier, a distant shifting surface where one great space environment yields to another. It lies far from the planet, but it belongs fully to Jupiter. It shrinks and swells with the solar wind, carries signs of exchange and instability, and reveals through waves and falling density that the spacecraft has moved into a new regime. In this region, Jupiter is no longer simply ahead. It is all around, shaping the space itself through a boundary that cannot be seen, cannot be touched, and yet decisively marks the beginning of the planet's own dominion. Inside the magnetopause, but still far from Jupiter's visible clouds, the spacecraft enters the middle magnetosphere. This is not a narrow shell or a brief interval. It is a broad, rotating magnetic world, immense in size and shaped less by the direct push of the solar wind than by Jupiter's own rapid spin, strong internal magnetic field, and the circulating plasma carried within that field. If the outer boundary marks the moment when Jupiter begins to rule the surrounding space, the middle magnetosphere shows what that rule looks like over a great distance. It is structured, restless, and mechanical in a planetary way, like a vast invisible engine turning through darkness. Jupiter rotates in about 10 hours. For a planet so large, that is very fast. The magnetic field anchored within the planet rotates with it, and the field tries to drag the surrounding plasma into the same motion. This tendency is called corrotation. Corrotation means rotation together, as if the plasma and the planet belong to one shared turning system. In the middle magnetosphere, that shared turning remains an important rule, but it is no longer perfect. The plasma does not always keep pace exactly. In some regions it begins to lag, meaning it falls behind the full rotational speed of the planet. That lag is not a small detail. It is one of the keys to understanding why Jupiter's middle magnetosphere becomes such a distinctive environment. The reason for that imperfect turning is simple in principle. Plasma has mass, even when it is thin. To keep it rotating at great speed far from the planet requires a continuous transfer of angular momentum, the rotational form of motion carried outward from Jupiter's spin. The farther out the plasma lies, the harder it becomes to enforce that rotation fully. The system does not stop rotating, but strain develops within it. Magnetic stresses grow, electric currents flow. The field lines are stretched and twisted by the attempt to make distant plasma move with the rapidly spinning planet. In this way, the middle magnetosphere becomes less like a neat dipole field, the kind often sketched around a simple bar magnet, and more like a broad and flattened magnetic disk. ESA describes this region as a magnetodisk, a stretched magnetic structure extending to hundreds of planetary radii. This flattening matters because it changes the geometry of the whole region. Instead of a rounded magnetic form, the middle magnetosphere develops a strong equatorial character. Much of its plasma and current is concentrated in a broad sheet near the equatorial plane. NASA-supported studies describe a thin equatorial current sheet as the dominant structure of Jupiter's middle magnetosphere. A current sheet is a region where electrical current is concentrated in a relatively thin layer. In Jupiter's case, the currents flow around the planet and also radially through the sheet, in patterns connected to the effort to keep plasma rotating. The environment, therefore, is not only magnetic in the abstract sense, it is electrical as well, with large current systems threading through the region and linking distant space back to Jupiter's upper atmosphere. Within this broad disk, motion remains organized but not quiet. The plasma sheet can thicken and thin. It can shift northward or southward away from its usual near-equatorial position. Galileo observations show that during one interval the plasma sheet is displaced northward for about 30 hours, leaving the spacecraft in a different magnetic hemisphere for several Jovian rotations. That kind of shift reveals that the middle magnetosphere is not rigid. It changes shape as forces rebalance within it. The twisting of the magnetic field also changes with distance from the current sheet. Near the equator, the flows are found to lag corrotation, while at higher latitudes the field pattern can reflect different behavior. This layered structure gives the middle magnetosphere a sheared quality, as though different parts of the same rotating system are not moving in exactly the same way. The solar wind has not disappeared here, but its role is different from the role it plays outside the magnetopause. In the middle magnetosphere, The dominant energy source is not simply the external wind from the Sun, it is Jupiter's own rotation. ESA describes the transfer of angular momentum from the fast-rotating planetary magnetic field to the space plasma environment as the engine that drives the Jovian magnetosphere. That description is useful because it shows why this region feels distinct from simpler magnetospheres. The system is internally powered on a vast scale. It behaves less like a passive shield and more like a rotating machine that must constantly redistribute energy, motion, and plasma through its own structure. That redistribution is not immediate. One of the quieter but important findings from simulation work is that the middle magnetosphere can respond slowly to changes in the interplanetary magnetic field. In one NASA report, the response time to such changes exceeds 30 hours. For a region driven strongly by internal rotation, that slow response makes sense. The middle magnetosphere is so large, and its own circulation is so substantial, that outside disturbances do not instantly rewrite its configuration. They arrive, press, and influence. But the region answers on its own scale of time. This gives the middle magnetosphere a kind of inertia, not only of matter, but of structure. Once set into a broad pattern, it does not surrender that pattern quickly. For travel, this region would be difficult even without invoking the denser plasma nearer the inner system, or the stronger radiation farther inward. A spacecraft here must operate in a rotating magnetic environment with large electrical currents, shifting plasma sheet geometry, and field structures that are stretched and stressed over immense distances. Orientation, measurement, and interpretation all become more complicated because the environment is neither empty nor uniform. It is possible to move through it, as robotic spacecraft have done, but the movement is through a system with its own internal dynamics rather than through passive space. A crewed craft would have to endure not only the duration of the voyage, but also the demands of existing inside a vast electrodynamic structure that never truly stands still. So the middle magnetosphere is Jupiter expressed as motion. It is the giant planet's spin made visible only through instruments, its magnetic field stretched into a disk, its currents gathered into sheets, and its rotational power transmitted outward through plasma, across distances that would themselves count as major regions in any smaller planetary system. Here, far from the clouds and still far from the deepest inner hazards, Jupiter already feels complete in one essential way. It has turned surrounding space into part of itself. The spacecraft is no longer merely near a planet. It is moving through a rotating extension of the planet's own energy and order. Within Jupiter's broad rotating magnetosphere, one region stands out because it is not supplied mainly by the distant Sun, and not by ancient leftover particles drifting inward from space. It is supplied by a moon. At the orbit of Io, Jupiter's innermost large moon, a dense ring of ionized matter circles the planet. This ring is called the Io plasma torus. A torus is a donut-shaped form, and the word is useful here because the region wraps around Jupiter along Io's path like a glowing band. Though its light is too faint and specialized to resemble an ordinary ring seen by the eye, in physical terms it is a zone of unusually rich plasma, meaning gas whose atoms have lost or gained electrons and therefore carry electric charge. Inside the middle magnetosphere, this torus forms one of the clearest signs that Jupiter's space environment is being fed from within its own moon system. Io is the reason. It is the most volcanically active world known in the solar system. Its surface is continually reworked by eruptions that release large amounts of sulfur-bearing material. Io also has a thin atmosphere made largely of sulfur dioxide. On its own, that atmosphere is delicate and patchy. But Io does not travel around Jupiter in isolation. It moves inside Jupiter's powerful magnetic field, and Jupiter rotates so quickly that its magnetic field sweeps past Io faster than the Moon moves in its orbit. This relative motion matters greatly. As the magnetic field rushes by, it strips material away from Io. NASA describes the rate as about 1 ton each second. That material does not remain neutral for long. Sunlight, particle impacts, and electromagnetic processes remove electrons and turn much of it into ions and free electrons. The result is a growing cloud of charged sulfur and oxygen around Io's orbital path. Because the source lies along Io's orbit, the charged material is not spread evenly through all nearby space. It gathers into the torus. The shape is not exact like a manufactured ring, but the broad image is correct. A thick, encircling band of plasma surrounds Jupiter where Io travels. This makes the torus one of the densest plasma regions in Jupiter's magnetosphere. Compared with the more rarefied magnetic environment farther out, the torus is rich with particles. Space there is still a vacuum by ordinary human standards, yet it is crowded enough in plasma terms to become a distinct domain with its own behavior, its own waves, and its own electrical character. The torus is not static. Jupiter's rotation tries to carry the plasma around with the planet in the same general sense that it carries other magnetospheric plasma. But the newly supplied matter from Io must first be picked up by the magnetic field. Pick up in this context means that neutral atoms become ionized and are then forced into motion by electric and magnetic forces. This is not a gentle handover, it is an energetic process. Fresh ions are accelerated, and in being accelerated they alter the surrounding plasma as well. The torus therefore becomes a place where supply, acceleration, and circulation are all active at once. It is one of the clearest examples in the solar system of a moon loading a planet's magnetosphere with new matter. Its composition gives it a particular identity. Much of the material comes from sulfur and oxygen derived from Io's volcanic gases. Those ions exist in different charge states depending on how many electrons have been removed. Electrons themselves are abundant as well. Together they create a plasma that responds strongly to magnetic fields and supports many kinds of wave activity. Instruments flown through the region detect this richness directly. The torus has long been known as a source of strong emissions in ultraviolet wavelengths and radioplasma signatures. It is not only a band of matter, it is a band of electrical behavior, radiating information about its density, temperature, and motion to any instrument built to listen. The torus also reveals a quiet truth about Jupiter's magnetosphere as a whole. Many planetary magnetic environments are imagined as shields holding the outside world away. Jupiter's cannot be understood only in that way. It is also a collector and processor of internal material. Io continuously feeds it. That feed changes the mass of plasma that Jupiter's rotating magnetic field must move. It changes current systems. It changes the shape of the magnetic disk. It changes the energy budget of the surrounding space. The torus is therefore not an isolated curiosity near one moon. It is a central working part of Jupiter's larger magnetic machine. A spacecraft passing through or near the torus would not meet a wall or a sharp visible band. It would instead enter a denser and more electrically active plasma region. Instruments would register enhanced ion and electron populations. Surface charging could become more significant. The electromagnetic environment would become harder to treat as simple background. The difficulty here is not pressure in the ordinary atmospheric sense, and not contact with a solid hazard. It is persistent immersion in a charged medium whose particles are fields and waves are more concentrated than in much of the wider middle magnetosphere. For human travel, this is another reminder that Jupiter is not surrounded by empty approach corridors. Even its inner moon region can fill space with active material that steadily works on hardware and measurements. The link between Io and Jupiter is also direct in a deeper electrical sense. Magnetic field lines connect Io's orbital region to Jupiter's upper atmosphere. Along those lines, currents can flow, coupling the Moon and the planet together. Some of the ions from the torus are pulled along magnetic paths into Jupiter's atmosphere, where they contribute to auroral activity. This does not make the torus merely an orbiting cloud left to itself. It is part of an electrodynamic relationship, meaning a relationship governed by moving charges, currents, and magnetic forces. The Moon supplies matter, the planet supplies the dominant field and rapid rotation, and the torus becomes the visible expression of that partnership in plasma form. So the Io plasma torus is a ring-shaped province of charged volcanic matter, suspended along Io's orbit inside Jupiter's magnetosphere and continually renewed by the activity of the Moon. It exists because Io is volcanic, because its gases can be stripped and ionized, and because Jupiter's immense, fast-moving magnetic system captures that material and turns it into a persistent electrical band. In this region, Jupiter's inward journey becomes more intimate and more strange. A moon feeds a planet's surrounding space. Darkness holds a donut of invisible charged matter, and the road inward passes not through emptiness, but through a ring built grain by grain, atom by atom, from the breath of the most volcanic moon in the solar system. Deeper inside Jupiter's magnetic system, the environment changes from active plasma to something more concentrated and more destructive. Here lie the inner radiation belts, broad donut-shaped regions around the planet's equator where charged particles are trapped by Jupiter's magnetic field and driven to extraordinary energies. A radiation belt is not a solid ring, and not a cloud in the ordinary atmospheric sense. It is a region where fast particles remain confined by magnetic structure, spiraling along field lines, bouncing between magnetic hemispheres, and drifting around the planet again and again. Around Earth there are radiation belts as well, but at Jupiter the scale and intensity are much greater. The giant planet does not merely possess stronger belts than Earth. It possesses one of the harshest trapped particle environments anywhere among the planets. These belts are filled mainly with electrons, protons, and heavier ions. An electron is a very light negatively charged particle. A proton is a heavier positively charged particle found in atomic nuclei. Ions are atoms or molecules that have lost or gained electrons and therefore carry charge. At Jupiter, these particles come from more than one source. Some ultimately trace back to the solar wind. Some are supplied from within the Jovian system, especially through material released by moons and later processed by the magnetosphere. Once present in the inner magnetic environment, the particles can be accelerated to very high energies. Jupiter's magnetic field, rapid rotation, and large-scale electric processes together make the planet act in some ways like a natural particle accelerator. What makes the inner belts so important is not simply that they exist, but that trapped particles can remain there for long periods and keep gaining or maintaining high energy. Magnetic fields guide the motion of charged particles. Instead of flying off freely, many particles spiral around magnetic field lines while also moving back and forth between northern and southern magnetic regions. At the same time, they drift around the planet. This combination of motions keeps them confined. The belts are therefore not fed once and emptied quickly. They are sustained structures, replenished and energized over time. The result is a persistent environment in which radiation is not a passing event but a standing condition. Near Jupiter, the highest fluxes of energetic particles are found in equatorial belts. Flux means the amount of particle flow passing through an area. High flux matters because it tells how many energetic particles a spacecraft or a human body is likely to face. It is not only the energy of each particle that causes trouble. It is also the number of particles arriving and penetrating material. In Jupiter's inner belts, both the energies and the particle counts can become severe. Spacecraft systems passing through these regions are steadily struck by particles that can pass into components, alter signals, disrupt memory, and damage electronics over time. The hazard is cumulative in one sense and abrupt in another. Some effects build slowly. Others happen as sudden glitches when a single energetic particle strikes a sensitive part. This is one reason Juno is designed so carefully around Jupiter's radiation. NASA places the spacecraft in long polar orbits that avoid the strongest parts of the equatorial belts as much as possible. Rather than circling around Jupiter in the same broad equatorial zone where the radiation is worst, Juno dives in over the poles and passes between the belts and the cloud tops. Even with that strategy, the environment remains dangerous enough that the spacecraft carries a titanium radiation vault around much of its sensitive electronics. The vault is not a luxury. It is an admission by engineering that ordinary spacecraft protection would not be enough. Radiation near Jupiter can age hardware, degrade sensors, corrupt data, and threaten the entire mission if not treated as a central design problem from the beginning. The inner belts also resist simple shielding. Radiation is not a single substance that can be blocked by one universal wall. Different particles interact with matter in different ways. Some can be stopped by relatively modest shielding. Others penetrate more deeply and produce secondary effects when they strike the shielding itself. Stronger shielding also adds mass, and mass is costly in spaceflight. This means protection becomes a compromise. Engineers do not build a perfect fortress around a spacecraft. They decide what must be shielded most carefully, what materials to use, and what risk can be tolerated. At Jupiter, the fact that even heavily protected missions must worry about radiation reveals how powerful the environment truly is. For living tissue, the problem becomes more serious still. Energetic particles can pass through cells, break chemical bonds, damage DNA, and increase the risk of illness and long-term injury. Acute exposure at sufficiently high levels can harm the body quickly. Long exposure at lower but still significant levels also carries danger. In Jupiter's inner belts, the environment is so severe that an unprotected human mission is not realistically imagined there. The issue is not discomfort or manageable operational caution. It is biological hazard on a scale that turns brief exposure into a major survival problem. A human traveler would not experience this region as spectacular light or visible flame. The harm would come invisibly, carried by particles too small to see and too energetic to ignore. The belts also change how spacecraft behave even when they remain functional. Sensors can register false events. Cameras can be peppered with bright streaks caused by penetrating particles rather than actual light from the scene outside. Computers can suffer bit flips, where stored information changes because radiation strikes electronic memory. Materials can darken, weaken, or lose performance. Over time, solar cells, detectors, and circuit elements can all age faster under radiation assault. The spacecraft therefore moves through a region that steadily tries to confuse it, tire it, and wear it down. It is not only a matter of surviving one crossing, it is a matter of enduring a continuous rain of invisible impacts. Jupiter's inner radiation belts are also not perfectly simple in structure. Juno data show that the region contains unexpected features, including radiation zones closer to the planet than earlier models emphasized. This does not alter the main truth. It deepens it. The belts are not only intense, they're still being mapped in detail, and their exact three-dimensional distribution is shaped by magnetic geometry, particle sources, and the presence of moons and rings. Observations indicate structure and variation within the larger pattern, even while the overall environment remains consistently hostile. So, in the inner belts, Jupiter's one-way character becomes harder and more exact. Distance and gravity have already made the journey demanding. Here, trapped high-energy particles turn space itself into a long-lasting hazard. The belts surround the planet not as decoration, but as an invisible siege. They attack electronics, burden engineering, and place living tissue in direct danger. They do this continuously, without sound, without heat that can be felt through the hull, and without any obvious visual warning. In this region, Jupiter no longer appears merely remote or massive. It becomes actively unwelcoming through a form of violence written into magnetic confinement and particle energy. A violence quiet enough to be missed by the senses and strong enough to define the fate of any craft that dares remain too long within it. Closer still to Jupiter, after the great magnetic structures and the deepest inner belts have already claimed space around the planet, matter begins to show itself in a gentler but more delicate way. It does not appear first as a solid surface, because Jupiter has none. It does not appear as a sharp atmospheric wall, because the giant planet's outer edge is gradual. Instead, the first material layers are subtle. They're made of dust, thin neutral gas, and the quiet persistence of particles that too sparse to resemble clouds and too real to be called emptiness. In this region, Jupiter's outermost matter is present, but it is present lightly, as if the planet begins not with a border, but with a fading in. The rings are part of that beginning. Jupiter has a ring system, though it is easy to miss because it is so faint. Saturn's rings announce themselves with brightness and broad icy structure. Jupiter's do not. They are composed mostly of very small, dark, sparse particles that reflect little light. Against the brilliance of the planet, they nearly disappear. Only careful imaging and favourable geometry reveal them clearly. Their faintness is not a minor visual detail. It tells what they are. These are not thick, gleaming sheets of icy blocks. They are dusty, delicate structures made of material so fine and so thinly spread that light passes through them with little return. The system is commonly described in three broad parts. There is a flat main ring. Inside that lies a thicker, more diffuse halo, shaped less like a sheet and more like a swollen inner cloud. Outside the main ring lies the gossamer ring, a very faint outer extension. Observations from Galileo show that this outer region actually includes two overlapping gossamer components associated with different source moons. This gives the whole ring system a layered character. It is not one neat band. It is a family of dusty zones, each shaped by source material, orbital motion, and the electromagnetic environment around Jupiter. Their origin is now understood in a simple and elegant way. Interplanetary meteoroids strike Jupiter's small inner moons. These impacts blast dust from the moons into surrounding space. Because the moons are small and their gravity is weak, some of that debris escapes and remains in orbit around Jupiter. The main ring is associated with the tiny moons Metis and Adrastea. The more diffuse outer gossamer material is associated with Amalthea and Thebe. In this sense, the rings are not ancient objects preserved unchanged from the birth of the solar system. They are maintained by ongoing damage. Small impacts keep feeding them. Dust is lost, dust is replaced, and the rings survive as a continuing process rather than as a static monument. Because the ring particles are so small, they do not simply behave like miniature moons. Dust grains respond not only to gravity, but also to sunlight, to plasma, and to electric charge. A grain can become electrically charged in Jupiter's radiation environment. Once charged, it becomes more responsive to magnetic and electric forces. This helps explain why the halo is thicker and more cloud-like than the flatter main ring. The region near Jupiter is not a quiet stage on which dust moves only under gravity. It is a place where tiny grains are continuously modified by impact, charging, and the surrounding magnetic system. The rings are therefore physical and fragile at once. They exist, but they are always being worked on by the environment that surrounds them. A spacecraft entering this region would not strike a rigid barrier of ring matter. The rings are far too sparse for that kind of encounter to resemble crossing a wall, yet they would still matter. High-speed impacts with even very small grains can damage surfaces, pit coatings, or threaten sensitive instruments. A sparse ring is not harmless merely because it is sparse. Relative speed in space gives tiny particles unusual importance. The danger here is statistical rather than dramatic. It comes from dust that is difficult to see, spread over a broad region, and approached at velocities that turn small grains into energetic projectiles. Mixed with this dusty ring region is the outermost fringe of Jupiter's atmosphere. Here the word exosphere becomes useful. The exosphere is the uppermost, most tenuous part of an atmosphere, where particles are so far apart that collisions become rare and the gas gradually blends into surrounding space. On a giant planet, this edge is especially difficult to treat as a line. Jupiter's atmosphere is made mainly of hydrogen and helium, and at the very top those light gases become extremely thin. There is no exact point where atmosphere stops and space begins. Density simply falls and falls until the distinction becomes one of convention rather than touch. The exosphere is therefore not a shell that can be landed on or passed through in a single moment. It is a fading margin. That fading margin matters because it means Jupiter's beginning is not sharp. The planet does not wait behind a fixed surface. Its neutral gas already extends outward in a form that is extremely tenuous but still planetary. Atoms and molecules in this region can be struck by sunlight, altered by charged particles, and in some cases ionized or nudged onto new paths. Some may remain bound, some may be lost slowly to space. Jupiter's gravity is so strong that the upper atmosphere is held more tightly than the upper atmospheres of smaller worlds. Yet the outermost edge still remains a place of continual exchange rather than perfect stillness. The exosphere is not thick enough to feel like air, but it is not nothing. This makes the region between rings and exosphere especially subtle. Dust and gas coexist without blending into one ordinary medium. Ring grains orbit in flattened and diffuse bands, while neutral hydrogen and helium form a very thin atmospheric fringe around the planet. Both are faint, both are easy to overlook beside the brilliance of Jupiter's cloud tops, yet both mark the first material presence of the planet itself. After so much invisible structure deeper in the magnetic environment, matter now begins to appear in forms that are almost whisper-like dust, too sparse to shine brightly, and gas too thin to become cloud. This quietness should not be mistaken for safety. Dust can strike. Thin gas can charge surfaces and affect measurements when combined with radiation and plasma. Most of all, the region confirms something fundamental about Jupiter. There is no clean doorway from space into the planet. There is only a gradual thickening of matter. First the dust rings, faint and replenished by impacts. Then the uppermost fringe of hydrogen and helium, where the atmosphere begins as a near vacuum and slowly becomes more substantial. Nothing here invites a landing. Nothing offers a firm start of the world in the way a rocky horizon would. So the rings and upper exosphere form Jupiter's first material edge, though edge is almost too hard a word for something so gradual. Dust lifted from small inner moons circles in dim bands around the planet. Above the deeper atmosphere, neutral gas extends outward until it is scarcely different from space itself. In this region, Jupiter begins to take on physical form not as ground, but as delicacy. The giant planet starts with a veil, not a boundary, and the road inward passes through dust and thinning gas before any deeper atmosphere can truly be said to begin. Above Jupiter's visible cloud tops, the planet enters a region that is thinner, hotter, and more electrically active than the calm appearance of the bright bands below might suggest. This is the upper atmosphere, and in the part relevant here, two features stand out above all others. One is the aurora, the great polar glow produced when charged particles plunge into the atmosphere along magnetic field lines. The other is the thermosphere, the high atmospheric layer where temperature rises strongly with height, because energy is deposited there from sunlight, particles, electric currents, and atmospheric motion. At Jupiter, these two are closely connected. The auroras are not only lights over the poles, they are signs that energy is pouring into the upper atmosphere, helping to make this region one of the strangest and least intuitive parts of the planet. The word aurora is familiar from Earth, where northern and southern lights ripple in the sky near the poles. On Jupiter, the same general process occurs, but on a much grander scale. Charged particles are guided by the planet's magnetic field into the upper atmosphere near the magnetic poles. As these particles strike atoms and molecules, they transfer energy. The atmosphere then releases some of that energy as light. At Jupiter, the main gases are hydrogen and helium, so the resulting glow differs from Earth's oxygen and nitrogen auroras. Much of Jupiter's auroral activity is especially strong in ultraviolet and infrared wavelengths, rather than in the ordinary visible light that human eyes use best. The auroras are real, but their richest forms are seen most clearly by spacecraft and telescopes designed to detect those wavelengths. They are also persistent. Earth's auroras can brighten and fade with solar storms, but Jupiter's auroras are often present continuously because the planet's magnetic engine is continuously active. Material from Io feeds the magnetosphere. Jupiter rotates rapidly. Electric currents link the magnetosphere and the upper atmosphere. As a result, the polar regions are not waiting for rare outside events to become luminous. They are part of a standing electrodynamic system. Brightness changes, shapes shift, flares appear. Yet the overall auroral activity remains a regular feature of the planet rather than an occasional spectacle. The main auroral oval forms a ring around each magnetic pole. This oval marks the region where large-scale currents and particle precipitation are especially strong. Inside and around it lie more complex emissions, including bright spots and irregular patches. Some of these are associated with the magnetic connection between Jupiter and its moons. Io, Europa, and Ganymede can each leave signatures in the auroral pattern, because their interaction with Jupiter's magnetic field sets up currents that connect back to the planet's atmosphere. In this way, the auroras are not only local weather in the upper air, they are maps of a wider system, showing where the giant planet, its magnetic field, and some of its moons remain linked by moving charge. The upper atmosphere receiving this energy is extremely thin compared with the dense gas deeper down. Yet thinness does not mean weakness. Because the region is so exposed, and because energy arrives in such concentrated ways, the thermosphere becomes very hot. The thermosphere is the atmospheric layer where temperature rises with altitude because high-energy radiation and particles are absorbed there. On Jupiter, this heating is surprisingly strong. Observations indicate that temperatures in the upper atmosphere rise far above what sunlight alone should produce at Jupiter's great distance from the Sun. This has long been one of the important puzzles of the giant planet's atmosphere. The upper air is too hot to be explained by solar heating alone. Several processes are understood to contribute. Auroral particle precipitation is one. As electrons and ions rush down into the polar upper atmosphere, they dump energy directly into the gas. Electric currents flowing through the ionized part of the atmosphere also generate heating. This process is often called Joule heating, meaning heating produced when electrical energy is dissipated through resistance. Strong winds and atmospheric waves can then move some of that energy away from the poles. Observations indicate that these mechanisms together help explain the remarkable warmth of Jupiter's thermosphere. It remains uncertain exactly how the heating is distributed across the planet and how efficiently polar energy spreads toward lower latitudes. But the basic truth is steady. The upper atmosphere is hotter than simple sunlight can account for, because Jupiter's magnetic and electrical activity continually feeds it. This makes the thermosphere unlike the quiet top of a simple atmosphere. It is not merely the last thin trace of gas before space. It is an active interface where space conditions and atmospheric conditions meet. Charged particles arrive from above. Neutral gases respond below. Some of the gas becomes ionized, meaning that electrons are stripped away and the atmosphere becomes partly conductive. Once conductivity is present, electric currents can flow more easily, coupling the atmosphere to the magnetosphere. The thermosphere is therefore both atmospheric and space-facing at once. It belongs to the planet, but it is constantly shaped by processes that come through the magnetic system overhead. Hydrogen dominates this region as it dominates Jupiter more broadly. One especially important form is the triatomic hydrogen ion, written by scientists as H3+. It forms under energetic conditions and radiates strongly in infrared light. This emission helps researchers measure temperature and motion in the auroral thermosphere. It also reveals how energy is being deposited and redistributed. The gas itself remains thin, but its radiative behavior makes the upper atmosphere visible to instruments in a very informative way. In Jupiter's auroral zones, the thermosphere can therefore be studied not only as hot gas, but as glowing, moving, electrically influenced gas. For travel, this region would be deceptive. It is far above the deeper atmosphere and too thin to provide lift or ordinary aerodynamic control in the familiar sense. Yet it is not gentle. A craft passing through the uppermost atmosphere over the poles would encounter energetic particles, electrical effects, heating processes, and rapidly changing local conditions tied to auroral activity. The danger would not resemble flight through thick air. It would be more like passage through a hot, rarefied, electrically active boundary layer where the atmosphere still exists but already behaves in close partnership with space. Instruments could be confused. Surfaces could charge. Thermal control would become more difficult because heating is not coming only from sunlight or motion through gas, but from the planet's broader electrodynamic environment. The auroras also give this region a sense of constant motion without requiring visible storm clouds. Curtains, arcs, spots, and rings brighten and shift over the poles as currents and particle flows change. The thermosphere below and around them responds with temperature changes, winds, and pressure variations in the thin gas. None of this is loud in the human sense. It is a calm violence. expressed through energy transfer rather than impact. Light appears where particles strike. Heat rises where currents and collisions deposit power. The upper atmosphere glows because the magnetosphere does not leave it alone. So above Jupiter's cloud tops, the planet reveals a high atmospheric region ruled not by familiar weather first, but by magnetism, charged particles, and heat. The auroras mark the places where that influence enters most clearly, drawing polar rings and patches of emission into the thin gas. The thermosphere holds the energy of those interactions, remaining far hotter than weak sunlight alone should allow. In this region, Jupiter's upper atmosphere is not a quiet ceiling over the planet. It is a living boundary where the giant world receives energy from its surrounding magnetic system and turns that energy into light, temperature, and motion high above the hidden depths below. Below the very thin, hot upper atmosphere and above the main cloud deck lies Jupiter's stratosphere, a region less dramatic in appearance than the auroral thermosphere above it, yet no less important in shaping what the planet looks like from afar. The stratosphere is a layer of atmosphere defined by its temperature structure. In a stratosphere, temperature rises with height rather than continuing to fall. On Jupiter, this layer sits above the deeper weather region and contains thin hazes, trace gases, and photochemical products made when sunlight and energetic particles alter simpler molecules. It is not a place of solid surfaces or sharp boundaries. It is a filtered region where light is sorted, chemistry is refined, and the atmosphere begins to take on a layered delicacy above the heavier clouds below. The clearest physical impression of Jupiter's stratosphere comes from haze. Haze is made of extremely small suspended particles, finer than ordinary cloud droplets or ice crystals. These particles can scatter and absorb light in ways that reveal their presence even when the deeper atmosphere remains hidden. NASA observations show that the very high-altitude haze stands out strongly when Jupiter is viewed in ultraviolet and near-infrared wavelengths. In ultraviolet light, gases above the clouds scatter sunlight so strongly that the deep-banded cloud layers become hard to see, while the high haze shows up against the bright background. In the near-infrared, methane gas absorbs strongly, darkening the background and making the same high-altitude haze appear relatively bright. These reversals are useful because they show that the haze is not merely a faint visual tint over the planet. It is a real atmospheric layer, present high above the main clouds and detectable because of the way it handles light. This haze is not spread evenly across Jupiter. High-altitude haze is seen especially over the poles and along the equatorial region. The polar hoods are among the most distinctive examples. A polar hood is a broad cap of haze covering high latitudes, giving the poles a softened, slightly muted character in some wavelengths and a darker, more absorbing appearance in ultraviolet views. Recent Hubble monitoring continues to track features within these polar hoods, including dark ovals visible only in ultraviolet wavelengths. These are not deep cloud storms in the familiar striped weather deck. They belong to the stratospheric haze region itself, which means the stratosphere is not a passive blanket laid over lower weather. It has its own structure, movement, and regional differences. The chemistry of the stratosphere explains much of this. Jupiter's atmosphere is made mainly of hydrogen and helium, but methane is also present in smaller amounts. High in the atmosphere, methane molecules are exposed to sunlight and near the poles to additional energy from auroral activity. When methane is broken apart, the resulting fragments can react to form more complex hydrocarbons. Hydrocarbons are molecules made of hydrogen and carbon. Some remain gaseous. Others contribute to the formation of tiny aerosol particles, which are small, suspended solids or liquid droplets. In Jupiter's stratosphere, these products become part of the haze. NASA describes the polar stratosphere as a place where energetic auroras heat the stratosphere and stimulate the formation of complex hydrocarbons from the breakup of methane molecules. That simple chain of events ties light, chemistry, and structure together. Sunlight and energetic input alter methane. Chemistry builds new compounds. Those compounds help create haze. The haze then changes how the planet appears and how radiation moves through the upper atmosphere. Because the particles are so small, the haze behaves differently from the deeper clouds below. A cloud deck is often composed of larger particles or droplets that form a more sharply defined layer. Haze is finer, more diffuse, and more sensitive to atmospheric motion. It can remain suspended at high altitude for long periods. It can be stretched by winds, confined within particular latitude bands, or concentrated in regions where chemistry and circulation favor its growth. This is why the stratosphere often appears smoother than the deeper cloud layers in visible images, yet more intricate in ultraviolet views. The larger storms below produce bold contrasts and familiar belts and zones. The haze above traces subtler motion, often revealing waves, caps, and ovals that belong to a higher level of the atmosphere. One striking NASA observation from Cassini imagery shows that Jupiter's polar stratosphere can produce a dark vortex wider than Earth. The feature develops within the ultraviolet visible haze and behaves in ways that make the high atmosphere visibly dynamic. Its existence shows that the stratosphere is not simply a chemical shelf resting above the weather. Winds and shear operate there as well. Shear means a difference in wind speed or direction across space. In Jupiter's stratosphere, shear can stretch, deform, and transport haze patterns. The high atmosphere therefore carries its own kind of meteorology, though it is gentler in appearance than the giant vortices and belts seen at cloud-top level. Temperature structure matters too. The defining characteristic of a stratosphere is that it becomes warmer with height. On Earth, this happens largely because ozone absorbs ultraviolet sunlight. On Jupiter, the details differ because the atmosphere is chemically different, but the principle of radiative heating remains. Sunlight absorbed by gases and haze particles, together with additional energy sources at high latitudes, helps create a warmer layer aloft. This rising temperature with height suppresses the kind of overturning motion that dominates deeper convective regions. Convection is vertical mixing driven by buoyancy, where warmer material rises and cooler material sinks. In the stratosphere, stable temperature structure resists that kind of vigorous overturning. The result is a more layered atmosphere. Air still moves, waves still travel, and haze still shifts, but the region remains more stratified than the turbulent weather deck below. That layering has a visual effect on the whole planet. The stratospheric haze acts like a filter over the deeper atmosphere. It can soften contrasts in some wavelengths and emphasize them in others. It can partly hide what lies below, especially when viewed in ultraviolet light. In this way, Jupiter's face is not created only by the clouds that reflect sunlight. It is also shaped by the thin haze above them that modifies the path of light before it escapes to space. What looks like a simple bright planet through a telescope is therefore a stack of layers, each adding its own optical signature. For any spacecraft trying to study or cross this region, the stratosphere would not feel like a surface or a dramatic threshold. It would be a gradual change in density, composition, and radiative behavior. The gas remains thin compared with the deeper atmosphere, yet it is thick enough to host chemistry, carry haze, and respond to winds. Instruments looking downward would see changing transparency depending on wavelength. Instruments sampling the gas would find trace compounds and suspended particles, rather than only the simple hydrogen and helium expected in a cleaner upper atmosphere. The difficulty here is subtle. The stratosphere does not crush. It filters, shapes, and conceals. So Jupiter's stratosphere is a quiet high layer where chemistry and light do much of the work. Methane broken by sunlight and energetic input helps produce complex hydrocarbons. Those products form fine haze. The haze gathers strongly over the poles and equator, drifting and reshaping under high-altitude winds. Temperature rises with height, keeping the layer relatively stable compared with the deeper convective atmosphere below. In this region, Jupiter becomes softer in outline but richer in structure. Above the bright cloud world, a thin veil of chemistry and suspended particles turns the giant planet's upper air into a place of filtering light, slow motion, and layered atmospheric refinement. At the level of Jupiter's visible face, the planet at last seems to offer something familiar. There are clouds, bands, colour, and motion that can be seen directly. Yet even here, familiarity remains only partial. The cloud tops of Jupiter do not belong to a sky above land or sea. They are the highest bright surfaces of a planet with no solid ground, a weather deck suspended over greater depths of gas and fluid. From far away, these clouds give Jupiter its most recognizable appearance: broad alternating stripes, pale zones, darker belts, and scattered vortices turning within them. This is the part of Jupiter most easily imagined, because it can be photographed and watched. It is also the part that reveals how unusual the giant planet truly is. The visible atmosphere is not a calm skin. It is a moving pattern written by jet streams of enormous scale. The highest main cloud layer is thought to be made largely of ammonia ice. That is the first important fact about the cloud tops. These are not water clouds like those familiar on Earth. They form in a colder, chemically different atmosphere dominated by hydrogen and helium, with ammonia playing a major role in the upper visible deck. This gives the cloud world a different physical character from any earthly weather system. The clouds are bright because they reflect sunlight well, especially in the lighter zones, but their brightness does not mean simplicity. Tiny changes in altitude, chemistry, and particle size can alter how much light is reflected, what colour emerges, and whether a given region appears pale, tan, brown, orange, or white. The most striking pattern is the sequence of belts and zones that wrap around the planet parallel to the equator. A zone is a brighter band. A belt is a darker one. The pattern continues across much of the globe, though it becomes less regular toward the poles. These bands are not painted onto the atmosphere. They are expressions of motion. Each band is associated with large east-west winds known as zonal jets. Zonal means that the flow runs mainly along lines of latitude, circling the planet rather than moving directly north and south. The visible stripes, therefore, are not static stripes at all. They are the appearance of an atmosphere being divided, stretched, and maintained by powerful alternating jet streams. Where one jet meets another, the atmosphere experiences shear. Shear is a difference in speed or direction across neighbouring regions. On Jupiter, shear helps sharpen boundaries between belts and zones. Some bands host rising motion and thicker high clouds. Others reveal somewhat deeper and darker layers because the upper cloud cover is thinner. This is one reason the zones often look brighter while the belts look darker. The bright zones tend to be regions where high ammonia clouds are more extensive. The belts often show lower, less reflective material or thinner cloud cover, allowing darker tones to emerge. The exact colour-producing compounds remain uncertain, but observations indicate that sulfur, phosphorus, and carbon-bearing chemistry may contribute to the richer browns, reds, and oranges. What is clear is that the colours do not float independently of the winds. They are tied to circulation, cloud thickness, and the movement of air across latitude bands. The jet streams themselves are extraordinarily strong. They race around the planet at speeds that can exceed several hundred kilometers per hour, and they maintain their basic latitudinal structure over long spans of time. This endurance gives Jupiter a paradoxical appearance. The atmosphere is always moving, yet the global pattern remains recognizable year after year. Belts can fade, revive, narrow, broaden, or shift in color, but the underlying banded architecture persists. The planet therefore combines stability and unrest in the same visible surface. It is not chaotic in every sense. It is orderly on the larger scale and turbulent within that order. Within the bands, turbulence takes many forms: cloud streets, plumes, ovals, and twisted filaments appear where flows interact. Some regions show neat boundaries, others become visibly shredded, with streaks and curled textures that resemble cream stirred through darker liquid. This imagery helps because Jupiter's visible atmosphere often behaves as though many nearby currents are sliding past one another at different speeds. The familiar banded face is not made of flat-coloured strips. It is made of active cloud systems being stretched by jets, rolled into vortices, and continually reworked by atmospheric motion. Even where the large pattern looks simple from a telescope, close views from Juno reveal that the cloud tops are richly textured and full of local variation. There are also places where the ordinary banded arrangement begins to break down. NASA's recent Juno images show regions known as folded filamentary regions, where the usual zonal jets weaken or lose their clean structure and the clouds become more chaotic. In these areas, the familiar stripes give way to irregular, tangled patterns that can evolve over only a few days. This is important because it shows that Jupiter's visible atmosphere is not uniformly governed by the same clear band logic everywhere. The jet system is powerful, but not identical in every region. Where it falters or becomes disturbed, a different visual language appears, one of folds, knots, and rapid local change. Storms also inhabit the cloud tops, though in this section the main point is not their depth or long-term history, but their place within the visible weather deck. Vortices form where neighbouring flows interact, especially where shear is strong. Some rotate for long periods, others are smaller and shorter-lived. The Great Red Spot is the most famous example, but it is only one member of a broader family of visible Jovian vortices. The cloud tops provide the stage on which these storms are seen, outlined by colour contrasts and bounded by jets that help sustain or reshape them. A storm on Jupiter is not simply a disturbance in otherwise calm weather. It is part of a constantly moving atmospheric tapestry. Light also changes the meaning of the cloud tops. Sunlight reflects from high clouds and is absorbed differently by deeper or chemically distinct regions. This is why Jupiter's face can appear subtly different depending on wavelength. In visible light, the bands and vortices are already striking. In other wavelengths, contrasts shift. Hidden structure emerges, and haze or ammonia abundance changes the view. But even in ordinary sunlight, the cloud tops carry enough information to reveal the atmosphere's main organizing principle. The visible world of Jupiter is a world of differential reflection shaped by moving gas. For travel, these cloud tops would present a deceptive image. They seem almost like a surface because they are bright, continuous, and sharply patterned. Yet they are not a place to stand or land. They are the upper visible part of a gaseous atmosphere, without firmness beneath the eye. A descending craft would not meet a crust hidden under the beauty, it would meet moving cloud, variable density, strong winds, and no clear transition from sky to ground. The cloud tops therefore offer an illusion common to giant planets. They look like a face, and yet they are only weather. So at the level of Jupiter's visible atmosphere, the planet becomes most recognizable and most misleading at once. The upper clouds, likely rich in ammonia ice, reflect sunlight into bright zones and darker belts. Powerful zonal jets divide the globe into long-running bands, while local turbulence, filaments, and vortices complicate the pattern from within. The overall design endures, even as details change from day to day. In this region, Jupiter's outer beauty is inseparable from motion. Its stripes are winds made visible, its colours are circulation made luminous, and its cloud tops are not a resting place, but a restless weather deck spread across the largest planet in the solar system. Below Jupiter's visible cloud tops, the atmosphere does not suddenly turn into ground, it simply continues. The bright upper deck of ammonia ice gives way to deeper gas, thicker cloud layers, and steadily rising pressure. This is the region where Jupiter becomes most difficult to imagine using habits formed on rocky worlds. On Earth, descent suggests approach to a surface. On Jupiter, descent means entry into increasing depth with no firm landing place ahead. The atmosphere grows denser, warmer, darker, and more compressed, and each change arrives as part of a continuous transition rather than as a clean threshold. The first important truth in this deeper region is that the visible cloud tops are only the uppermost weather surface, not the full depth of the weather itself. Juno's gravity measurements show that the banded belts and zones are not shallow painted features. They extend downward for about 3,000 kilometers. That depth is astonishing because it means the familiar striped appearance belongs to a vast outer weather layer, not to a thin decorative skin. The winds seen at the top are therefore tied to motion far below, and a descending craft would remain inside the same broad atmospheric engine long after the visible patterns above had faded from sight. As pressure increases, the chemistry of cloud formation changes. The uppermost visible ammonia clouds do not represent the only cloud layer. Planetary atmosphere studies and the Galileo probe data support the expectation of a deeper sequence. Below the ammonia cloud level, a cloud layer associated with ammonium hydrosulfide is expected, and deeper still, water clouds can form where temperatures and pressures allow water vapor to condense. These deeper layers matter because they show that Jupiter's atmosphere is not uniform gas from top to bottom. It is structured by condensation, chemistry, and vertical motion. Different substances form clouds at different depths, and each cloud layer marks a zone where rising and sinking gas meets changing temperature and pressure in a new way. The Galileo atmospheric probe offers the clearest direct glimpse into this region. It enters Jupiter's atmosphere in December of 1995 and returns data for about 58 minutes before its transmitter fails under increasing pressure and temperature. The probe descends into what turns out to be an unusually dry hotspot rather than an average part of Jupiter. Even so, it reveals a world of fierce winds, sparse upper water compared with expectations, and a deep atmosphere that remains active well below the visible cloud deck. By the time the signal is lost, the probe is enduring about 22.7 atmospheres of pressure. That is already enough to show how rapidly Jupiter's atmosphere becomes physically severe. Even before the deepest layers are reached, winds deepen with the atmosphere as well. Galileo records winds as high as about 640 meters per second. What is striking is not merely the speed, but the persistence. The winds do not fade quickly beneath the first cloud layers. They remain strong as the probe descends. This indicates that Jupiter's atmosphere is not arranged like a calm lower layer under a windy upper skin. Motion penetrates. The giant planet's weather is broad in the vertical sense as well as the horizontal one. Downward means not escape from weather, but immersion in a more massive part of it. As descent continues, light changes. Sunlight has already been filtered by the upper haze and clouds. Deeper down, the atmosphere thickens until the bright bands above no longer define the surroundings. The visual world narrows. Clouds may appear as layers, veils, or broken structures, but eventually the sense of moving through open sky gives way to movement through thickening gas where contrast is reduced, and downward vision has little meaning. There is no horizon in the earthly sense because there is no approaching ground to anchor perspective. The atmosphere itself becomes the setting. Temperature rises along with pressure. Compression is part of the reason. When gas is forced into a smaller volume, it tends to heat. Jupiter also radiates more energy than it receives from the Sun, which means the planet's deep atmosphere is not warmed only from above. Heat from within contributes to the thermal structure of the descending gas. This creates a powerful convective environment in many regions. Convection is the vertical overturning of fluid driven by buoyancy, where warmer material rises and cooler material sinks. In Jupiter's deeper atmosphere, convection can organize towering cloud structures, transport heat upward, and help mix gases between levels. The deeper one descends, the more the atmosphere resembles a deep fluid in restless motion, rather than a thin sky over something solid. Water becomes especially important in this deeper realm. In the upper atmosphere, water is difficult to measure because its abundance varies from place to place, and because cloud formation and circulation complicate direct interpretation. Juno's microwave observations help estimate that at the equator, water makes up about 1/4% of the molecules in Jupiter's atmosphere, roughly several times the solar value there. That result does not solve every question about Jupiter's global water abundance, but it confirms that water is a real and meaningful constituent of the deeper atmospheric layers. Where water clouds form, they can drive some of the strongest convective storms, because water condensation releases latent heat. The energy stored during evaporation and released when vapor condenses back into liquid or ice. This released energy can strengthen upward motion and make deep storm systems more powerful. The deeper atmosphere is therefore not only denser, it is more forceful. Pressure rises steadily. Gas presses from every direction. Temperature climbs. Wind remains strong. Convective storms can grow tall and violent in vertical extent, even if their upper signatures look modest from afar. Electrical activity is present as well. Jupiter does have lightning, and the deeper water-rich storm regions are thought to play an important role in producing it. A descending vehicle would move into a world where darkness, turbulence, and compression increasingly work together. Yet the most important feature of this whole region is the absence of any solid interruption. A craft descending below the cloud tops does not move toward a place where engines can hover above rock or ice. There is no deck beneath the storms, no hidden crust under the pressure, no ocean surface in the familiar sense waiting to be reached. The gas simply thickens. Density rises until the distinction between atmosphere and fluid becomes less intuitive, but there is still no boundary that would count as land. This is why Jupiter's deep atmosphere turns descent into an irreversible idea. Every kilometre downward means more surrounding mass, more pressure to resist, more heat to endure, and more energy that would be required to climb back through the same growing weight of gas. For machines, this progression is merciless. A vehicle designed for vacuum does not belong in thick gas. A vehicle designed for ordinary flight cannot rely on familiar lift in a region where pressure, turbulence, and temperature become extreme, and where the medium itself keeps changing character. Structures compress, materials weaken, electronics suffer, thermal control fails under mounting load. Even before the deepest parts of Jupiter are approached, the atmosphere has already become a trap made of continuity. There is no single catastrophic wall. There is only unbroken worsening. So in Jupiter's deep atmosphere, the planet reveals the quiet logic of its one-way nature. The visible clouds above are only the beginning of a weather layer thousands of kilometers deep. Beneath them lie additional cloud zones, stronger convection, growing warmth, thickening gas, and pressure that rises without offering any place to stop. The deeper atmosphere does not present a dramatic final barrier because it does not need one. It turns depth itself into the barrier. Descent continues, conditions intensify, and the ordinary idea of return fades into the same thickening medium that never becomes ground. Far below Jupiter's cloud tops and deep atmosphere, the planet enters a region where familiar distinctions begin to fail. Gas has long since thickened beyond anything that would be called air in an ordinary sense. Pressure has risen so greatly that hydrogen, the simplest and most abundant element in Jupiter, no longer behaves as a light gas alone. It is forced into denser forms. The deeper one imagines the descent, the less useful everyday language becomes. Jupiter is still made mostly of hydrogen and helium, but under immense compression these materials take on properties that belong to another physical regime. The planet remains continuous, yet its interior is profoundly transformed. Hydrogen is the key to this region. Near the top of Jupiter, hydrogen exists as a gas, its atoms moving freely and its behavior easy to recognize in principle. Deeper down, pressure rises until the atoms are crowded far more tightly together. Under those conditions, hydrogen is compressed into a liquid form. Deeper still, scientists think that the pressure becomes so great that electrons are squeezed loose enough for the fluid to conduct electricity like a metal. This state is called liquid metallic hydrogen. The phrase sounds strange because it joins two categories that seem separate in daily life. Hydrogen is usually imagined as a gas. Metal is imagined as a solid. Inside Jupiter, those categories no longer hold their ordinary meanings. A fluid can behave like a metal if its electrons can move through it freely enough. That is what matters here. The deep hydrogen becomes electrically conducting. This metallic region is one of the great defining features of Jupiter. It is not visible from outside and cannot be sampled directly by any current spacecraft. Yet its consequences reach all the way into space around the planet. Electrical conduction within a rapidly rotating fluid allows currents to flow. Those currents, in turn, are thought to generate Jupiter's magnetic field through dynamo action. A dynamo is a process by which the motion of an electrically conducting fluid creates and sustains a magnetic field. On Earth, a dynamo operates in the liquid iron outer core. On Jupiter, the conducting material is not molten rock or iron, but compressed hydrogen. The planet's rapid rotation, about 10 hours for one full spin, helps organize that flowing conductive region. The result is the immense magnetic field that extends millions of kilometers into surrounding space. In this sense, the deep metallic interior is not isolated from the outer journey already described. It is the hidden engine whose effects reach far beyond the planet itself. The pressure required for this state is extreme. It is far beyond the pressure in the deepest oceans of Earth, and far beyond the strength of any vehicle built for atmospheric entry. Pressure here is not merely a weight from above. It is compression from all directions within a planet holding itself together under its own gravity. The material becomes so compressed that ordinary chemical intuition becomes less helpful than condensed matter physics, the study of how densely packed matter behaves. In Jupiter's depths, matter is not arranged as clouds over open space. It is packed into a planetary interior where fluid motion, electrical conductivity, and thermodynamic change all interact continuously. Helium, though less abundant than hydrogen, also plays an important role in this region. Under deep Jovian conditions, hydrogen and helium do not necessarily remain perfectly mixed everywhere. Models and observations suggest that helium may separate from hydrogen in some interior layers and sink deeper downward in the form of droplets. This idea is often called helium rain. The phrase is useful as long as it is kept within context. It does not mean raindrops falling through an Earth-like sky. It means denser helium-rich material settling through a hot compressed fluid interior. As that material sinks, gravitational energy is released as heat. This helps explain why Jupiter radiates more energy than it receives from the Sun. The giant planet is not only warmed from above by sunlight, it still releases internal heat, some left from formation and some associated with slow, ongoing interior processes. In the deep interior, Jupiter is not cold and still. It remains thermally alive. That escaping heat matters because it helps keep the interior in motion. Warm material tends to rise, cooler material tends to sink, and within a giant fluid planet this encourages convection over enormous scales. Convection in the metallic region is not visible weather like the belts and storms near the top. It is slower, deeper, and hidden. But it may be even more important to the planet's long-term behavior. The deep fluid interior transports heat outward, while also participating in the dynamo that creates the magnetic field. Jupiter's interior is therefore not built as a stack of motionless shells. It is more like a graded fluid world in motion, with changing composition and changing physical states arranged by pressure, temperature, and gravity. At the center of this world lies one of Jupiter's most interesting uncertainties. For many years, scientists often pictured Jupiter as having a relatively small, solid central core made of heavier elements such as rock, ice, and metal, clearly separated from the surrounding hydrogen and helium. Juno has changed that picture. By measuring Jupiter's gravity field with great precision, the mission finds evidence that the core is much larger than once expected and not sharply separated from the surrounding material. Instead, the deeper interior appears to include a dilute core, sometimes described as fuzzy. The word does not mean vague in a careless sense. It means that the heavy elements may be spread through a broad inner region, rather than packed into one compact solid ball with a clean boundary. Observations indicate partial dissolution and mixing, with no clear dividing line between core material and the metallic hydrogen around it. This has a quiet but important consequence for how Jupiter is imagined. Even at the center, the planet may not contain the kind of sharply defined destination that rocky intuition expects. There may be denser material inward, and there may still be a central concentration of heavy elements, but the transition appears to be broad rather than abrupt. Jupiter does not merely lack a surface at the top, it may also lack a simple solid center at the bottom. The whole planet tends toward continuity, graded by depth and compression rather than divided into familiar separate worlds. That continuity is one reason the idea of descent on Jupiter never resolves into arrival. The deeper regions change in character, but they do not grant a final landing place. For any machine, these innermost layers remain entirely beyond survival. The temperatures are immense. The pressures are crushing beyond comparison. Materials would not retain their ordinary strength. Electronics would fail long before. Structure would be overwhelmed. A spacecraft attempting to descend this far would not encounter a dramatic final impact with a hidden flaw. It would be destroyed by conditions that intensify continuously until the concept of an intact craft no longer applies. Inward on Jupiter means deeper into a fluid planet whose matter has been transformed by gravity into states no surface vessel can endure. So the metallic interior and hidden core complete Jupiter's inward story by showing that the planet is not empty beneath its storms, but filled with matter made strange by pressure. Hydrogen becomes liquid and then metallic. Electrical currents move through the conducting depths and help generate the giant magnetic field. Internal heat continues to escape through slow, deep motion. At the center, heavy elements appear not as a neat solid kernel alone, but as a broader diluted inner region mixed into the surrounding mass. In this deepest realm, Jupiter becomes what it has been hinting at from the start, a world without a surface, without a simple bottom, and without any natural point at which descent turns gently into arrival. Jupiter remains where it has always been, far beyond the warmth and ordinary scale of Earth, turning in cold sunlight with its bands, storms, rings, and hidden depths. The journey inward has shown no welcoming shore, no solid coast, no place where motion ends in rest. Distance stretches the voyage. Gravity deepens the fall. Magnetic fields claim the surrounding space. Radiation fills the inner dark with invisible danger. Dust circles in faint rings. Thin gas becomes layered atmosphere. Clouds gather and shift. Pressure rises without pause. Heat builds. Hydrogen itself changes under the weight of the world. Even near the center, the planet does not offer a simple flaw, only deeper states of matter held in the long patience of gravity. So Jupiter becomes a place where return fades not through one sudden barrier, but through accumulation. Each layer asks more than the last. Each region removes one more familiar assumption. There is no single moment when the planet declares that passage must become one way. The truth emerges gradually, as light weakens, as distance lengthens, as atmosphere thickens, and as the world reveals that it is made not for landing, but for descent without end. And still, in the quiet of thought, Jupiter remains beautiful. Its remoteness gives it clarity. Its stripes hold their order across the turning globe. Its auroras burn above the poles. Its hidden interior powers a magnetic kingdom far beyond the clouds. It is severe, but not chaotic. It is unreachable in the human sense, yet understandable in part through careful observation, patient measurement, and the calm work of science. The giant planet turns. Its storms continue. Its deep interior remains under unthinkable pressure. And far away, in the smaller and gentler orbit of Earth, the mind can let the image settle into stillness of vast world without a surface, luminous in the outer dark, keeping its distance, keeping its secrets, and moving on through the long night.